In this video, we'll go over a technique for numerical integration called the Newton-Cotes Integration Formulas. After studying this video, you should be able to understand how the Newton-Cotes integration formulas are developed and estimate the error in an integral calculated using one of the Newton-Cotes integration formulas. Also, you should be able to implement the Newton-Cotes integration formulas in MATLAB. So let's start by talking about why we are interested in numerical integration. So one application would be to integrate discrete data directly. So you know how to integrate lots of functions from your calculus classes, but sometimes we just want to integrate data. Also, we can use numerical integration to calculate integrals of functions whose antiderivatives are difficult or impossible to determine analytically. And here's an example. This is the function that describes the normal distribution. And if you look at it, the main form of this function would be e to the x squared. So if we tried to take the integral of e to the x squared dx, there's no analytical solution. However, the area under this curve, that area, that's an important statistics measure. That's what gives us the confidence intervals that come from the bell curve Gaussian distribution. So it is a really practical calculation that we know exists, and this needs to be done numerically. A last application is to use numerical integration techniques in the development of differential equation solution algorithms, and we are going to start looking at that next week. So let's start by reviewing the definition of integration. If you recall from your calculus class, integration came from totaling the area under a curve, and you probably developed that by starting with a bunch of rectangles, each rectangle having a width of delta x and a height of f of x, and you started with a Riemann sum. The total area was the Riemann sum of the f of x's times the delta x's, and then you took the limit as delta x approached 0 of that sum, and that's what gives rise to the integral. I is the integral from a to b of f of x dx. So our main approach to calculating a numerical integral is just going to be similar to what we did for differentiation, to use a finite delta x. So let's now get into the Newton-Cotes approach for doing this. And the Newton-Cotes approach is to replace the function or tabulated data that's in the integrand with a polynomial, and we know polynomials are easy to integrate. So we'll take that function and just replace it with some nth order polynomial, and we can use our earlier material on interpolating polynomials to do this. So let's start with the trapezoid rule, and the trapezoid rule is what we get by taking our simplest approach and replacing the function or interpolating the data with a first order polynomial. So that first order polynomial would be the equation for a line. So we have the equation for a line, f1 of x here, as f of a plus fa minus fb over b minus a, and all times x minus a. And to calculate the integral, we're just going to integrate, put this function in here, and integrate that line from a to b. And so when we integrate that line from a to b, we're going to get f of a times x plus f of b minus f of a over b minus a, all times x minus a, squared over 2. And then evaluating that from a to b, and we'll plug in those results. So we get f of a times b minus a plus f of b minus f of a divided by b minus a times b minus a squared over 2 minus a minus a squared over 2. That term is equal to 0. The squared cancels with this b minus a, and simplifying, what we'll get now is b minus a over 2 times f of a plus f of b. And that's our result for the trapezoid rule. And the next thing that we want to do is know, well, how accurate is this single application of the trapezoid rule? So we know we're going to have some error. We can see it right here. Here's the error in the integral that we're going to in the integral estimate that we're going to have by modeling the function there that has some curvature as a straight line. So the error in the trapezoid rule can be shown to be primarily due to truncation error using the Taylor series. And the actual derivation of this is beyond our scope, but the end result is that the error is equal to negative 1/12 times the second derivative, and this is at a point, any point between a and b. That's what we mean by that Greek letter zeta. And proportional to b minus a cubed. So we see two things here. Neither is very surprising. The error depends on the size of the integration range. So what is the size of the range? And the curvature of the function. So the more the curvature the function has, the more it's going to deviate from the line that we're modeling the function with, or the underlying data, and that would increase the error. So this leads to two possible strategies for improvement. One would be to break the integration range into parts so that we would decrease that b minus a term. Another is to use a higher order interpolating polynomial. So let's look at both of those approaches next. The composite trapezoid rule is what we get by breaking the integration range into n evenly spaced intervals. So over in this figure, we've got 1, 2, 3 intervals that gives us 3 trapezoids, and you can see here that the error, this distance between the straight lines and the curve, we have reduced error, obviously, by breaking that up into parts. So what we'll do is just apply the trapezoid rule to each of those n parts and sum the results. So going through and summing those results, we'll break up that integral from a to b to go from some, call a x1 to x2, and x2 to x3, and x3 to x4. Or in general, if we have 3 regions, we're going to end the integration at some xn plus 1. Those 3 intervals would be defined by 4 data points. Doing each of those integrals, we end up with this result. And then if we assume that these are equally spaced integrals to simplify the equation, we will call the interval spacing h, and that's just going to be x2 minus x1. If those are all equal, it would also be, h would be b minus a over n. Then this equation simplifies to a composite trapezoid rule. I is equal to h over 2 times f of x1 plus twice the sum of all of the internal points plus the last function evaluation. And it makes sense that we have that 2 there, because if you look at doing our integral, we're going to use that function evaluation once, and then use the second function evaluation, and then we're going to reuse the second function evaluation for our second interval here. So that's why we get the 2 f of xi for the internal points. So let's look at the error behavior of this composite trapezoid rule in a more quantitative fashion. So we know that that error for a single application is -1/12 times f double prime times b minus a cubed. So for a single interval, we would have for the ith interval, the error is f double prime, again zeta is some value in that ith interval, times h cubed, where h again is the width of that interval. So to get the total error, et, we're going to sum this over n intervals, and what I'm going to do is just call this an average value of that second derivative, and h again is going to be b minus a over n cubed. And when we do that summation, all of these are constant. If we assume this is an average, again, evaluation of the second derivative, then these are all constants, so that summation just becomes a multiplication that we're going to multiply this term by n times. So this is equal to n times -1/12 f double prime bar, and then I'll break this up, b minus a cubed over n cubed, and we see that the n cancels out with one of those cubes and changes that to a square, and we can rewrite the truncation error for the composite trapezoid rule, simplifying as -b minus a over 12 times the average value of the second derivative, and now we brought out one of the b minus a's, and so it's just proportional to h squared. So this is going to be second order accurate with respect to our interval spacing, and also depending on the curvature of the function. And that's not too surprising. So the smaller intervals we use, the more accurate we get, and the less curvature of the function, the more accurate we get with the trapezoid rule. So the other approach that we said we could take for decreasing the error and making this approximation more accurate was to use a higher order interpolating polynomial. And that's the approach we use to get to Simpson's 1/3 rule. So if we use a quadratic Lagrange interpolating polynomial, recall that looks like this. So we're going to basically fit a quadratic through these points, and now we're going to capture some curvature. So we would expect it to be more accurate. We need some intermediate point, x2, in order to do this. So we need a minimum of 3 points sampled from our function. And that integral from x1 to x3 is, I'll spare you the algebra. So we'll plug this f2 in here, and we'll just say here's some algebra after we do the integration, and simplify and assume that it's equally spaced. In other words, x2 is halfway between x1 and x3. We end up with a final result for Simpson's 1/3 rule, and the reason it's called Simpson's 1/3 rule is because of this 3 right here. So we have h over 3 times 1 function evaluation at x1 plus 4 function evaluations at x2 plus 1 function evaluation at x3. So that 4, that's what shows up as a result of integrating that second order Lagrange interpolating polynomial. So let's look at the error in Simpson's 1/3 rule. So the truncation error estimate, again, this comes from a Taylor series analysis. And again, the details of that are beyond our scope. But we see that the truncation error is proportional to the fourth derivative and b minus a to the fifth. Again, that zeta is just saying we're evaluating that fourth derivative somewhere between the integration range a and b. So we see that the errors depend on the fifth power of the integration range, and that's compared to the third for the trapezoid rule. And again, one approach to make this more accurate is to break the integration into parts and have a composite Simpsons rule. So let's take a look at that. So for a composite Simpsons rule, we can set this up with a set of subintervals, just like we did with the trapezoid rule, but there's one key difference is each interval now has 3 points. So we need 3 points for each interval because we need 3 points to evaluate Simpson's rule. So recall Simpson's rule, we have h over 3 times f of x1 plus 4f of x2 plus f of x3. So looking back here at this figure, you can see we're going to have 1, 4, 1 for the first 3 points, so points 1, 2, and 3. Then we're going to have 1, 4, 1 again for points 3, 4, and 5, and 1, 4, 1 for points 5, 6, and 7. And the result is when we sum all of these integrations, so each of our regions look like this. There's 3 points for each region. And when we sum these regions, we're going to have, again, a single function evaluation at our first point for the range, a single function evaluation for our last point. So again, for our integral, that's usually a, and b for that integral from a to b. But then on the internal points, we're going to have, for the even points, we have 4 function evaluations, and that's just from, again, from that integration of the Lagrange polynomial, of the quadratic Lagrange polynomial. But for the odd points, we're multiplying those by 2, and multiplying those by 2 again because those odd points are getting counted twice at the end of a first interval and the beginning of a second interval. So they're counted twice. So this is the equation that we use to implement Simpson's 1/3 rule. And if we look at the error behavior, we can kind of derive what happens with the composite behavior compared to the single application in the same way we did with the trapezoid rule. And we see that that error behavior is fourth order with respect to the interval spacing h. And a key distinction here is we have 3 points, but our h is each interval for the Simpsons rule is over 2, involves 3 points there. So that's a key difference for Simpson's 1/3 rule. We could go further and use a cubic polynomial, and that gives us Simpson's 3/8 rule, again called 3/8 rule. I'm sorry, I misspoke over here. The h for this is not the full space of the interval. The h is still the data spacing. Sorry about that. That is the data spacing. not the full interval width. So that's different from the trapezoid rule where h was the interval width and the data spacing. So looking at Simpson's 3/8 rule, we would integrate a cubic polynomial over 4 points, and the end result has 3/8, and the internal points are each weighted by 3. And again, that just results from the integration. And it turns out that the error in Simpson's 3/8 rule is also proportional to b minus a to the 5th. So it's no more accurate. It's approximately the same accuracy as the 1/3 rule. And it's kind of beyond our scope to go and derive why that's the case, but we'll just take that result that it is proportional to b minus a to the 5th. The composite application would be order h to the 4th again. So the one use of Simpson's 3/8 rule is to use it at the end of a data range along with Simpson's 1/3 rule when the number of intervals is odd. So going back again to Simpson's 1/3 rule, a composite Simpson's 1/3 rule is we need an even number of intervals and odd points, odd number of points. And if we don't have that, if we're integrating data directly and we don't have control over how many points we have, we can use Simpson's 3/8 rule on one end of the integration to make up for it. We could go to higher order Newton-Cotes formulas, and in general, the higher the order of the polynomial we use, the higher the derivative of the function in the error estimate. So like Simpson's 1/3 rule is proportional to the 4th derivative, and the higher the power of the step size. So Simpson's 1/3 rule was proportional to b minus a to the 5th for a single application, or again that was 4th order for a composite application. And as in Simpson's 1/3 and 3/8 rule, the even segment odd point formulas are going to have truncation errors that are the same order as formulas adding one more point. So for this reason, the even segment odd point formulas, like Simpson's 1/3 rule, are preferred because they're computationally less expensive, but they give you about the same accuracy. So some final implementation notes. For one, when you're implementing discrete data, sometimes the data is not equally spaced. Recall, we assumed that the data was equally spaced. That's how we defined an H. But if it's not equally spaced, we have to change how we implement that. Now, one approach is to go back to the non-simplified form, and that's actually what MATLAB's built-in function for the trapezoid rule, trapz, does, and I'll talk more about how to use trapz in a future video, but it's basically going to implement that trapezoid rule in the form going interval by interval and not simplifying it using assuming equally spaced data. Another approach is to use a spline or some other interpolation technique to generate interpolated data that is equally spaced, and then use something like Composite, Simpson 1/3 rule. And a third option is to use a curve fit, but one note about the curve fit is the integration is going to tend to average out the errors rather than amplify them. And we'll see an example of this in a future video. So it's usually not that helpful to use a curve fit for integration, because when we're summing up those intervals with an integration, the positive and negative errors that we would have for a curve fit tend to average each other out. So the integration is doing the same thing as the curve fit in terms of the error behavior. One last implementation note is when we're integrating functions, we can sample that function. So recall that the way these Newton-Cotes formulas are working is by using a function to generate data or sampling that function at specific points and then calculating the integral from those function evaluations. So if we're using a Newton-Cotes formula to integrate a function, we could sample that function at any interval, which means we have control over the data spacing. And one nice thing that we can do with that is develop an adaptive algorithm which could be used to improve computational efficiency. So for example, we might here, this is the MATLAB humps function again, you might do just fine with a large interval for that range where the data is almost linear, but then use much smaller intervals near that sharp peak, and then again a larger interval, maybe a couple smaller intervals, and then a larger interval, a couple smaller intervals. And so we have a variable data spacing, and we get increased computational efficiency because we have less function evaluations to compute. And MATLAB actually uses adaptive Simpson quadrature in the quad function. So you can imagine the way that that works is it uses larger intervals in regions where the function is approximated well by that quadratic polynomial. Remember, that's the underlying function for Simpson's 1/3 rule. And then larger and smaller intervals where it needs to capture that behavior of the function. And the way that it basically works is it calculates the integral using one set of intervals and then a smaller set of intervals and compares the results to decide whether or not to use that smaller set of intervals or decrease it further. And we'll talk a little bit more about adaptive quadrature in a future video. But that concludes this discussion of the Newton-Cotes formulas for now.